All right. I guess there's now an echo because you could actually hear me. The reason why I'm using this is because this is a webcast course. So everything that I put up on the screen here and everything that I say is going to be recorded and it's going to be put on a website that you can actually get back to and look at later on. I don't know if I can fix that volume or so. But anyway, let me back up a little bit here. Okay, welcome to EE C245, ME C218, Introduction to MEMS Design. I'm sort of going through what I just said without the microphone, so I'm Professor Clark Nguyen, and I will be teaching this class. Okay, so a little bit about myself. So I actually got my PhD from this university, but a long time ago, so that was in 1994. After that, I actually went to the University of Michigan to teach for about 10 years or so. And I came back to Berkeley in 2006, so I've been here maybe 5 years or something like that. My research is exactly on the topic of this course. So this is the type of material that I love to teach, and I enjoy it quite a bit. At the UM and also at UC Berkeley, I've been teaching mainly circuit design courses, though. So my background, and some device courses and some process type courses. So that's sort of my EE type background. My background is more a circuit designer, an integrated circuit designer, who got a little bit bored with the transistor level design and so now wants to design in mechanics. Also circuit design, and that's a lot of what this class is about. It's a circuit design type class with a lot of technology included, a lot of physics. But fundamentally, the way I look at it is a way to design circuits of mechanics. Okay, and that's what I enjoy doing. So some of the courses that I've taught here at UC Berkeley, just to give you more perspective, are EE 140, which is the analog circuit design course, 143, which is the fabrication technology course for semiconductor fabrication, 243, which is an advanced level fabrication course, and finally 245, which is this course, of course. Okay, in 2001, I founded a company called Desera, so I have some business experience as well. I guess there may be some chairs way in the back there. And so this was the first company to commercialize a vibrating RF MEMS technology, which is what my research is about. And that is really my true love, things that, mechanical things that vibrate that you can then use to do signal processing for things like wireless communications. I guess I have some even more practical or at least funding agency research type experience in that from mid-2002 to 2005, I actually left Michigan temporarily to become a program manager at DARPA. DARPA is the Defense Advanced Research Projects Agency. They fund a lot of research, basically. So I was at that end. I was in Washington, D.C., giving money to lots of people, I suppose, is how to sum it up. But the topics of the programs that I sold and ran were things like power generation, chip-scale atomic clock, gas analyzers, which is sort of a sensor that's much better than the sensors that you could see out there, nuclear power sources, navigation-grade gyroscopes, on-chip microcooling, micro-environmental control. So I have a lot of experience in a wide array of different types of MEMS technologies. This course, though, is not going to look at that whole array. Right? This is the first course in MEMS. So we're going to look at some of the more fundamental things that you need to know before you can really get to that large array of different things that at least were supported under funding from 2002 to 2005. Okay? So today we're going to give a course overview, and I guess I just want to say a couple things about the goals of the course. The original goal is that it is accessible to a broad audience, and that's why it has minimal prerequisites. Okay, but beware that minimal prerequisites. That usually equates to a lot of suffering by everyone in the class at some point in the class. Okay, so you guys will have certain strengths. The EEs might have strengths in fabrication process technology or circuit design. The MEs might have strengths in things like free body diagrams and understanding stress and strain and that. All of these things we're going to be talking about. And so you're probably going to find yourself at a certain point in the course where you may not be as strong as a lot of the others on some of the topics we're talking about. It's a graduate course, so I'm not going to review a lot of that too much. So if you're missing some of that background, as a graduate student, you should be able to pick up a book and learn or relearn that material. So I'm sort of expecting you to do some of that. I won't just completely ignore the topic. I'll give an introduction to it, but a very, very fast introduction to it. Okay, so just be prepared to that. Be prepared to learn things that you probably have seen in the past, but just haven't been playing around with much at all recently, which means you'll have to pick it up again, and that means practicing some sample problems or something like that. Let's see, so this course has a design emphasis. So there's a lot of MEMS courses out there that are survey courses. They'll say, oh, you can do this, you can do that, nice pictures and that sort of thing. There'll be nice pictures in this class too. But this is more of a design emphasis. You're going to be learning the physics, you're going to be learning the details, and for that reason this is a graduate class. Okay? By the time you get out of here, you should be able to not only draw a nice picture of what you want to achieve, but also understand exactly what it can achieve, how you can make this thing move without touching it yourself, and how you can make this in a tiny size. Okay? The perspective of this course, I'm going to try to keep it as up-to-date as possible, so it'll be circa 2011 for MEMS research and commercialization. There are some related courses at UC Berkeley, and these are all courses, well, some of them are courses that would be nice for you to have taken at some point. So EE143, microfabrication technology. You may have had an equivalent course like this somewhere wherever you were. This is good to have as background here because a lot of MEMS is using the same fabrication technologies that are used for semiconductors, but now applying them to make mechanical structures and other types of structures, non-electrical structures. Okay, so it's good to have a course like this in your background. I'm basically going to go through 143, which I teach. Right? I'm going to take about 3/4 of the 143 material and do it in about 2 weeks in this class. That's how fast it's going to go. So hopefully you've had some of that in your background, or hopefully you're the type of person that can pick that stuff up fast. If you like reading novels and stuff, I think you can pick it up fast. Fabrication technology. That may be an exaggeration, but all right. 147 is Introduction to MEMS. That's our undergraduate course in MEMS, but it's kind of a fledgling course, so it's not. It's kind of a survey course right now. So if you've taken that course and you've seen a lot of stuff, a lot of broad range of stuff, but you haven't really seen a lot of the details, there are actually some seats way in the back in that corner there, if you want to squeeze in there, but very few seats, maybe 2. Otherwise, the floor in the front is a pretty good view. ME119, this is also a MEMS course, an undergraduate course, Introduction to MEMS. This also survey-like. This is actually a fabrication course in a lot of respects. I think Professor Li Wei Lin teaches this course, others out there. It focuses a lot on fabrication. So you could say it's a lot like EE's 143, except more focused on MEMS. There's bio courses, Bioengineering 121, Introduction to Micro, Nano, Biotechnology, and BioMEMS. And then there's another MEMS course beyond this one. Well, actually, they could be taken before this one. They're not really that related here. This is the ME version of this course on MEMS design. This is a lot on optimization is what this is talking about. Because we have all this array of courses here, this course is not going to say a lot about BioMEMS. Okay? So again, we're looking at fundamentals here, things that you'll need to understand in order to work with BioMEMS. We're going to sort of stray away from BioMEMS because that has a whole course by itself. Okay? Student background, I've been talking about that the whole time. Graduate standing, engineering, physical or biosciences. But if you don't have 143, you may suffer a little bit, at least in the beginning of this course. If you're not a good circuit designer or an analyzer, you will suffer at the end of this course. If you're not a good statics and dynamics person for mechanical engineering, you'll suffer right off from the beginning here. So, right, there's going to be a lot of suffering in the course, but you just have to be able to. It's going to be good practice for when you get out beyond your education here. You're going to have to do a lot of this kind of stuff. Okay, so what should you know? I guess, first off, it'd be great if you knew fabrication technology. So semiconductor fabrication technology. So if you're looking at this picture here, hopefully you recognize what this is. Okay, there may be some of you that don't. This is the cross-section of a CMOS fabrication technology. Okay, and so hopefully you can recognize that this is low-cost oxidation. It's kind of an old CMOS process, I guess, but it's got low-cost. These are the source-drain junctions. That's your gate. These are your interconnects above that. Hopefully you've seen this kind of stuff. If you have not, don't panic too much. Because again, learning this is like reading a novel. If you're the type of person who enjoys doing that sort of thing. I mean, that's how I characterize it, but we actually will go into some depth into the mathematics of, say, how thick this layer is, how well you can etch this, how straight that sidewall is going to be. Some of that's going to matter for our MEMS type fabrication coverage here. So you should either know this or be able to learn this quickly. Things like how to deposit or grow different types of films on an integrated circuit wafer. Okay, how to pattern or otherwise form shapes in the layers shown. So that means lithography and etching. What determines the order by which you put layers down and how you pattern them. Okay, so process technology, especially MEMS, is all about when you do something. There's only a few things you can do if you're doing a planar process. You can deposit a material, you can pattern it, you can deposit it, you can do an anneal, you can grow things. Right? When do you want to do things? That's the big question. And that's really all you have to be thinking about in order to get a certain cross-section. And so for this kind of stuff that we talk about in this class, we're going after a cross-section. This is a transistor cross-section. MEMS cross-sections are much different and arguably much more difficult to attain without things like stress and bending and that sort of thing. Okay, so we'll be talking a lot about this. This is one thing that if you know this already, you have an advantage. If you don't know it, you will be struggling in the beginning because I'm going to cover it extremely fast with the intention of forcing you to get it very quickly, which I think you can. And that'll have something to do with the textbooks that are offered for this course as well, which I'll talk about in a second. Okay, so what should you know? Continuing on this, you should know basic circuit analysis. Okay, and I mean some pretty basic stuff. And so I know that if you're an engineer, you've had this at some point in time. Let me do it this way. Okay, so for example, if you have this simple op-amp circuit here, okay, can you analyze this and tell me what this transfer function is? Okay, do you know how to analyze an op-amp circuit? And the answer is yes, you do, because I don't think there's any program out there, except maybe the bioengineering programs, I don't know, that does not have a Circuits 101 class or something like that, where you have to learn at least fundamentals of op-amps and how to do nodal analysis and that sort. Okay? So you should be able to do this. So what should you be able to do? So if you look at this circuit here, and if I say this is an ideal op-amp, you should first be able to write down for me what the properties of an ideal op-amp are. Okay, so if I wanted the properties of an ideal op-amp, this is what you start with. Okay? And these are properties that you can apply only when you have negative feedback. Okay, so what are those properties? Go ahead.
The current into the minus plus terminals is 0.
Excellent, yes. I have that as number 2 in my notes, so I'll put it there. So that basically means that the input resistance, Rn, is infinity. Okay, so if I look into this node of the op-amp, that resistance is infinite, if it's an ideal op-amp. Okay? What else? Voltage is 0 here. Exactly, yeah, except I'm going to write that a little bit differently. If I call that V minus and I call that V plus, then I'm going to say that for an ideal op-amp, V minus has to be equal to V plus. Okay? And so that comes about because you have infinite gain in this op-amp. All right, that's another thing that I can say with this, that the gain is infinite. So I can even say that the gain, A naught, is infinite, but that actually doesn't matter for us right now. When you're doing ideal op-amp analysis, you generally don't even care about what that gain is. Okay, but this infinite gain is what gives you all of these other properties. All right, finally, what's one more thing? Output resistance. Output resistance of an ideal op-amp is 0. Okay? So those are the basic principles of an ideal op-amp, and you should have seen those somewhere. And as has already been mentioned up front here, if you have these basic principles, if V plus equals V minus, then this node right here is going to be effectively ground. Right? So I could take that out and do this and call that a virtual ground. Okay, and now just with that, with knowledge of that and knowledge of the fact that the input resistance into the negative terminal and the positive terminal of this op-amp is infinite, I can solve this problem very, very easily. Okay, so let's go ahead and do that. Change color here. All right, so first thing I want to do, I want to know what this output voltage is. Okay, so I can write an expression for that output voltage. That output voltage is going to be whatever current is going through this thing here. I can think of this as one element. And I can think of the current going through that element. It's going to be minus the current going through this times whatever the impedance of that element is. Right? And so what's the current going through that? Well, VI is my input. VI is going to generate some current that I'm going to call II. Okay? I know that I have infinite resistance going into the negative terminal, so II has nowhere to go when it hits this node except up and through this and to the output. Okay, so I know that going through that whole thing is I sub I as well. All right, and so the voltage here is going to be equal to minus that I sub I times the impedance of that element, which I can just recognize as being this resistor RF in parallel with the impedance of that capacitor, which is 1 over SCF. Okay? And so that's my impedance there. Now I want to play some tricks to get this I sub I in terms of V sub I. Now if I just recognize that I call that virtual ground right here, that's basically ground, that means I've got V sub I applied across this resistor R1 straight into ground. Okay? So I can write for the current, I can erase 2. So I can write for this current I sub I, that's just going to be equal to V sub I divided by R sub 1, I guess I'm calling it here, divided by R sub 1. I plug that into the I sub I for this formula, and I end up with minus V sub I over R1 times this parallel combination RF with 1 over SCF, but I can expand that parallel combination to be RF over 1 plus S times RF CF. Okay, so now this is looking, I can now solve for V naught over VI, which is what I'm looking for as a function of S. That's minus RF over R1 times this quantity 1 over 1 plus S RF CF, which oftentimes we like to write in terms of a frequency. So that becomes RF over R1 is 1 over 1 plus S over omega naught, where omega naught is 1 over RF times CF. So this now becomes my solution that I got very quickly by just knowing the ideal op-amp rule and applying some circuit analysis techniques, basically nodal analysis throughout this whole thing. All right, so this is the kind of thing you should understand definitely by the end of this course. You don't need to understand it right now, actually. You should, because you had a course like that, right? But you have the whole semester to get to this point here, okay? Because we're going to do sensing circuits at the end of the course. All right, but that's a little bit of the background you're going to need. This is about as bad as it's going to get, okay? And so if you feel intimidated by what I just did, and so some of the EEs, I'm sure you're not intimidated at all. You think this is simple. Some of the MEs, it's natural to feel intimidated if you haven't looked at that for time and time again, okay? Don't worry too much about it. You can pick it up fast. You just got to pick up that textbook that you had, if you still have it, or get a new textbook from here or something, and relearn that. Yes?
The S just an I omega?
Yeah, the S is just a complex variable. It's just a J omega in the end. So I can even write that in for you somewhere here. It's the same as J omega in the end. Okay? And I went through that very fast. When we get down to it at the end, we may be talking about even deeper things than this, like noise and that sort, in which case you're going to want to really know your circuits, but that's at the end of all of this. Okay? So, after scaring you a little bit, let's now talk a little bit about what this course is about. And I guess I should have handed this out before I started all of this. So, what I'm about to hand out are a number of sheets. The first is the course information sheet that I'm about to go through. The second one is the syllabus for this course. And the third one is the way I'm going to grade this course, which I always find is a good thing to pass out at the very beginning. So I'll start here. So pass that around. Hopefully everyone can get one. If not, it's not going to matter because everything is on the web. Everything will be on the web, as I'm about to show you here. And so let me get out of this mode and bring up that handout. All right, so let's look at the course information sheet first. I guess first of all, let me just demonstrate. This is all on the web. Okay, so if you want to get to the course website, just Google EE245, and you get this. And just plop onto that. This is the course website. Everything I'm talking about is here, prereqs. Your teaching assistants, which I guess I could talk about while I go through the sheet, but let me do it right now. So your teaching assistants are Mr. Henry Barrow, who's sitting way in the back there. His hand is up. You have another teaching assistant, Mr. Brian Pepin, who's not here. One, because he's sick. Two, because he's got a class at the same time as this one here. And so your teaching assistants are your, I guess, your main source of help for things like homework and that sort of things. And they will also be running your discussion sessions in this class. You'll find them particularly helpful when we get to things like software. Okay, we plan to be using CoVentureWare during this semester, and so there's going to be a lot of things where you have to learn how to use those tools. But anyway, the website is up and running. Everything is there. You see links to things like lecture notes. This is where the notes will be posted. Like after this class, you'll see a PDF there. In addition to this, I also will post the modules that come along with the lectures. The way that I will do the lectures is as follows. So you've seen this here. This is a module that I'm sort of lecturing out of. This is something that I'm going to put online so that you can actually look at what type of material I'm going to be covering even before I cover it. But I do not lecture entirely out of these modules. Okay, these are just a nice compact way to put the information together that I'm going to talk about. The way that I'm going to lecture a lot of the time is through this technique here. Okay, so I'm actually going to do this, and let's see if I can. Yeah. So this is sort of the mode that I intend to lecture in. I'm actually going to have, some things where I can type things in, but the rest of it I'm going to be writing. And you're going to see it written in real time all up on this screen here, and it's all going to be recorded through webcast at the same time. Why do I have two screens? Because sometimes, say I have a picture of something that I'm working with on this side, I want to keep that picture up and point to it. And so I'll be writing on this side, pointing to the picture or circuit or whatever on the other side. I find this two-screen approach to be good. That's the problem with doing things by computer. On the board, I can draw something there, put something here, and that sort of thing. You can't do it on a computer with just one screen up, so I make two of them in PowerPoint. Okay? That's how I'm usually going to be doing these lectures, but today, no, because there's a lot of this sort of thing. Okay, so you have this course information sheet. It has all the data that you need there. There's my location, 574 Corey Hall. Don't be embarrassed if you can't find my office for 10 minutes or so. It's kind of hidden. Corey Hall actually is, it is laid out correctly in terms of how the numbers go. Let's go back to this because it may be good for you to know exactly how to get to my office. This seems silly for me to even do this, but it is a problem for some people. So Corey Hall is sort of shaped like this box, right? And fifth floor Corey Hall sort of has this thing where you can go around this and see the offices. The elevators are right here. Okay, my office actually is behind the elevators. All right. So that's where my office is right here. To get to that office, of course, you get off the elevator and you go this way. The problem is the numbers may fool you. Right? So they actually are numbered correctly because number 501 is right here, and it goes all the way around this thing to finally get to 574. It is actually in the right order, but it's not very intuitive. Okay, so that's how you get to my office there. All right, so I'll have office hours. I'll have twice a week for 1 hour, one on Monday, 2 to 3 p.m., another on Wednesday, 11 to 12. Your homeworks are going to be due generally on Tuesdays or Thursdays. Okay, so that's why I put them either before one of those homework due dates. Your teaching assistants, Henry's going to have his office hours Tuesdays, 10:30 to 12 a.m. This is going to be in 382 Corey Hall. Brian, also 10:30 to 12 a.m. on Thursday, though, in 382 Corey Hall. We might have to change some of these if you guys have problems getting to those office hours, because it is a problem having them at the same time on a Tuesday and Thursday, because if someone's got a class during that period, then you can't go to any of those office hours. So let me see a show of hands of those who need that changed. If you cannot make one of the office hours. Okay, that's not a lot for the TAs. Can you make one of the, like one of mine? A half hour of mine? Okay, well, we'll see how that works. We'll see how much of office hours you actually use. People do use my office hours a lot. Okay, so please come by. That's how I get to know you, etc. Okay, also come to the TAs. Maybe Henry and with Brian, we have to change some of this here so that everyone. So what the problem is, of course, it's from 10:30 to 12 or something like that. Okay, it's going to be 11 to 12:30 probably. There's no 10:30 to 12, right? So you have a little snitchet that you can go and see Henry and Brian, right? There's a small snitchet there. Okay, so we may just have to move this just a little bit. Which way should we move it? 10 to 11:30? Would that solve it? I think so, because the class is going to be from 11 to, yeah, okay. So one of you guys, Henry or Brian, you'll do it? 10 to 11:30? Okay, so Henry's going to do it. And can you note that down? All right. So you know where the lecture is. The discussion is 4 to 5:30 p.m. and 241 Corey on Monday evenings. Okay, so it's no longer evening. Sort of is, past 5 or so. Whether they really go an hour and a half, you'll see, right? So a lot of them will be 1 hour and that sort of thing. And this is going to be the method by which you learn. Well, you get help on homework, plus you get some of the more practical applications that I have no time to cover during the lecture. All right, so office hours, let's see, course description, you can read through that, but I'm going to sort of go through a description of what MEMS is today, so I won't go through that there. Prerequisites, we just discussed that, graduate standing, but it's better if you've had some background in some of these things that I talked about. Textbooks, okay, so the required text is this text by Centuria. Okay, so this is Steve Centuria, he's from MIT. He's been in the MEMS field for a long time. I think this is, if not second edition, at least something that's been edited to get rid of some of the errors that used to be in the book. Okay, is this the perfect book for this class? No. Is there a perfect book for this class? No. That's often the case when you have a graduate class, because you're learning stuff that's right on the edge, and there's no textbook that covers everything that we're going to cover. That's definitely true in this class. The Centuria book is kind of nice because it's fundamental. Okay, you can look at a lot of other texts in MEMS. They're kind of survey texts. They don't go deep enough. They don't talk about energy and co-energy, system type design and that sort of thing. Those are the things we want to learn about. Centuria does go into those, but he also does it in a way that I don't like either in some things. And so we'll change things up, parts of the class. The lectures will be very important. They're webcasts, so if you have to miss some lectures, you can always go and catch up on some of those. There's some supplementary texts that I have. So there's one by Greg Kovacs, Micro Machine Transducer Source Book. I think that's in the bookstore. That's a nice text because it gives you a lot of the applications. And it gives you a very wide array of applications, but it also doesn't go into a lot of depth. Okay, so that's why we're not using that as the course textbook, but it's a good thing to have and read through and learn from, because you see the very wide, diverse set of applications you can have in MEMS. There are a lot of other references on reserve on MEMS as well, like Changlin Liu's book, Malouf, who does a great job with especially processing technology, and a number of other textbooks out there. These are all textbooks that I would call more survey-like textbooks as well, okay, which is why we're not using it in the class necessarily. Another textbook I want to mention is this book by Jaeger. Okay, this is the book that's used in EE 143, the Semiconductor Processing Technology class. If you are not strong in semiconductor processing technology, get that book. Okay, it's a very thin book. It is like a paperback book. It's like a novel. Okay, that's why I liken it to a novel. I think it reads fast, but if you need to learn process technology and you haven't taken a course like 143, you could pick up that book and I think very quickly get process technology. That, together with the lectures that I will be doing, should make you strong enough in that area for this class. Okay? So Jaeger, that is in the bookstore as well. I imagine you don't care if they're in the bookstore, right? These days. Yeah, no one cares because you just buy your books off Amazon anywhere or something off the web, right? Yeah, it's cheaper. That's what I've been told at least. All right, so reading assignments and problem sets. Let me talk about those now, but let's talk about those in the context of the syllabus for the class. You have this syllabus with you. This stuff is all online too, so if you don't actually have this in your hand because there weren't enough copies, this is all online. So this is basically giving a calendar showing the lectures and the material that's going to be covered in each of the lectures. I don't claim to be able to stay on this syllabus necessarily. We will inevitably fall behind on this with questions and other logistical things. So whether we actually reach to the very end of this, I'm not sure. But we'll get close. And we'll try to stay close with this. Whether we're on this or not, this is showing the lecture material. It's also showing the reading assignment in the various textbooks associated with this class. Okay, so S stands for Centuria, J stands for Jaeger. If you want the Jaeger textbook, I at least tell you which chapters to read so that you can do a proper review of the process technology. But you can see Centuria throughout this, plus a lot of handouts here that I'll be passing out to supplement the material that's in Centuria. Okay, and so just taking a look at what we go through in this class, this is administrative information background today. We'll then talk about the benefits of scaling. MEMS is all about scaling and how you can get advantages by making something, simply making something smaller. You can get enormous advantages in certain performance parameters. You may get some minuses in others, so you have to engineer around that. So that's part of MEMS. It's sort of the art of engineering around what goes bad when you make something small, but at the same time harness in a big way what goes good. Okay, that's sort of my definition of MEMS. And so we'll talk about scaling, then we'll talk about how we do the scaling on the wafer level. So here's where we talk about fabrication technology. These weeks right here, or these lectures right here, fabrication process modules 1, 2, that's pretty much what we're doing to go through 143. All right? I may, in fact, take a little longer than this, maybe one more lecture longer than that, but it's going to be fast. You'll learn everything they learned in 143 in this very compressed time here. At that point, we'll then move on to more MEMS-centric fabrication processing. So this is the basics. These are modules like oxidation, deposition of films, lithography or so. At this point, we'll talk about surface micromachining, bulk micromachining. These are sort of using those modules to put together into a process flow that achieves a certain mechanical structure that you want on chip or off chip or what have you. And so we'll do a lot of processing up front, a lot of fabrication technology up front. Once you know how to make all these things, we'll then go into learning about the problems with fabricating these things. So mechanics of materials. The reason why MEMS in many ways is more difficult than CMOS is because you have to deal with stress and strain. Things can bend out of the plane when you don't expect them to, and you have to learn to control that. In the end, CMOS, I think, is a lot more difficult than MEMS if you know how to control stress. MEMS, usually you have just 3 or 4 masks, 5 mask processes. CMOS, how many masks? Device guys. You can have up to 40, right? A lot of masks in CMOS now. So CMOS is a much more difficult technology to do than MEMS. So if you're a MEMS researcher, never cry about your process, right? CMOS is much more difficult, all right? But MEMS is only easy when you know how to control things like stress and that. So you will learn how to do that in this class. We'll go through a lot of this mechanics of materials here. Then we'll start talking about how to actuate these things, right? Because if you have a tiny structure, you don't want to actuate it by physically pressing on it, right? There's really no good way to do that. Usually you have to actuate it by applying voltages. And so we have to think about transducers, things that convert energy from one domain, like the electrical domain, to another, the mechanical domain. Okay, so we'll study transducers, lossless transducers. You could see a couple lectures in there. You could see a midterm exam right there on the 27th. I guess I'll just talk about that right now. So we're going to have one midterm in this class and one final exam and a project, okay, plus lots of homeworks. Okay, your midterm is going to occur on this day. And pretty much we've held to the dates in the past times that I've taught this class. So you can pretty much assume it's going to be this day, the 27th. There's an outside chance it could be the first, depending on how people are feeling and where we are in the class. But usually it's where we say it is, and that's the 27. Okay, so the material that will be covered up to this midterm is all material that's up to a week before the midterm. Okay, so you can think that it's going to be equivalent circuits, dynamic mass, stiffness, that sort of thing. Okay, but more on that when we get there. After that midterm, transducers, equivalent circuits. Okay, so how to model mechanics using circuits. And so this is almost one definition of MEMS designer or researcher as well. Is that in circuit design, we're able to design huge transistor circuits, right? Your microprocessors and that sort. And we do that because we have models for the transistors, but they're simple enough models that you can put them together into huge networks of these things. Okay, that's something that EEs do very well. Right? It's something that MEs don't do very well, okay? Because MEs are more physicists, I suppose, in that they like to look at the details. And when you look at the details, it's hard to make something that uses lots of elements. Okay? So part of what we're doing in this class is we're going away from the traditional details and simplifying the models as much as we can. We're going to take a mechanical structure that looks like it's a complicated structure and equate it to a very simple electrical circuit. And then we're going to be able to take that electrical circuit and simulate it, automatically design it, all sorts of things, just like we do transistor circuits. Okay, so this class is like taking mechanics and using the mechanics the same way we use transistors. And that's a lot of what MEMS designers do. When you can make something small, you can make a lot of them. You can make a huge network of them. And that's what you have to learn how to do here if you want to be a good MEMS researcher. Okay? So these equivalent circuits will be very important. But once we do the mechanical circuits, we then want to interface these with transistor circuits. Okay, and so that's where sensing circuits comes along. So at a certain point, we'll be thinking, okay, we got the mechanical structure, we've built it, we can move it all sorts of different ways, or can sense all sorts of inputs that we want to sense. But we now need to be able to sense that and process that through digital circuits. And so there's got to be some transistors there that are going to pick up that signal. So there's where the circuit design comes in. We're not going to do complicated transistor circuits like you have in 140 or 240. A lot of them will be op-amp based. But we will, if we have time, try to get into noise. Right? Because noise is really what you worry about for sensors. Right? In a sensor, you want to get the smallest signal possible. Right? If you want to detect, say, motion sensor, the presence of someone who just moved, right? That input signal is going to be very small. And you're only going to pick up that input signal if your noise level is very small from your transistor electronics. And even from your mechanics. So mechanics has noise too. So we'll look at noise from all sides, and we'll try to figure out whether we can sense a tiny amount of motion or sense a tiny gas particle or something like that, using the theory that we'll talk about here. Okay, we'll talk about resolution. One of the sensors we'll look at very closely is gyroscopes. And finally, at the end of this, we have this last week where we do nothing, and we're not allowed to do anything. Right? This is called our Reading, Recitation, Review Day. We didn't used to have this. 2 years ago, this did not exist, and I could have used this time to talk about more lecture material, but now we don't have this time. And so this is your time to relax. It's actually your time to finish your project in this class plus all your other classes. Okay? Your final exam is going to be Tuesday, December 13th. From 8 to 11 a.m. That's exam group 5, which you can find all of this on the web as well. We're going to hold the final on this day. This is nice. It's a nice early day for the final. Usually this class has a final at the very end of finals week. But this is one of the first final days. Okay, you may not like that either because that gives you less time to study. But hey, you have vacation time right here. Lots of time there to study. All right, so on this syllabus, I've also done my best to indicate dates that I know I'm going to be gone. Okay, so we're all doing a lot of research here. I definitely am doing tons, so I need to travel quite often. And the nice thing about this class is it's being webcast. And so this star here shows a date that I know I'm traveling. I guarantee that's not the only date, just other dates I don't know about. Right? When a funding agency says, okay, you're going to this, I can say nothing but, okay, yeah, I'm going. Right? And so there'll be other days that I miss. When I miss these days, what I'm going to do is set up a makeup lecture that you can actually physically come to. But because this is a webcast, I don't think I need to guarantee that you can physically come to it. It's going to be webcast, recorded, everything. And so if you can't physically come to it because you have a class that overlaps or it's too late in the evening or something like that, then you can always watch the webcast. Okay, that's how we'll handle missed lectures. Last semester, I don't remember how many lectures I missed. Maybe I missed 3 total. Maybe 3 total or so. So it doesn't have to be that bad, but it could get bad, but I do my best to prevent it from doing that. Okay, so this is the syllabus. Let's go back to the course information sheet here. Problem sets, you're going to have a number of homeworks. Usually we have about 7 over the whole semester. So that's not a lot, right? If it's an undergraduate class, you'd have 14 once a week. So here we have some homeworks are 1-week homework, some are 1.5, some 2-week or so. Because they're conceptually more difficult than the undergraduate type assignments. So you'll have more time to do them. It's going to be a classic thing as a grad student, though. You're going to have to learn to manage your time. Right? If you're one of those who wants to wait to the very last day to do your homework, then a 2-week homework assignment you're not going to like at all. Because you're now doing this very long assignment in one evening, which is possible. People have done that before. And I'm not criticizing the last day homework thing, right? I mean, if you can do that, that's not a bad skill. But you can suffer quite a bit doing that. Okay, so you decide what you want to do. We'll have a project that I'm going to assign during the latter half of the course. In the past, I've had different types of projects. I've had projects where you design something very specific, like a gyroscope. I've had projects where they're completely open-ended, where maybe you find something you like, and you write something up on it, and do a presentation on it. It has to be something where you shrink the size to get some advantage, which is sort of what MEMS is all about. Okay? Anything else I should talk about? I talked about all those. Computer accounts. Okay, if you're an EE, you already have a computer account. Okay, and you should be able to use that account. If you need more disk storage space, then I can ask the department to get some storage space specifically for this class. How much storage space are you given as an EE student? Anyone know? Henry, do you know? How much storage space do you have if you get an EE account? 60 gigabytes? Yeah, that should be enough for this class. But if you need more, we can always get more. If you're a mechanical engineer, you probably don't have an account on the EE-type computers that will house the software that we'll be using. And so you should follow this to get an EE account. It's all an electronic thing. You have to get onto a website, type in new account on corey.eeks.berkeley.edu, and you should be able to go through this process to get an account as you need it, okay, for this course. Finally, grading policy. This is the way I'm going to split things up. So problem sets will be 20%. The project is 25%. The midterm is 20%. The final exam is 35%. Okay? This has worked well in the past, very well in the past, so I think I'm going to stick with this. Regarding grades, you have a sheet here that talks about grading and normalization procedure. You can read through that and see exactly how I do it. I do it by taking a Z, sort of statistical Z score here, where I take the actual grade that you get on the thing, say like this is the exam. I subtract the average, I divide it by the standard deviation. What that does is it takes all the grades and makes the average 0, and the one standard deviation is a 1. Okay, so it makes it very easy for you to figure out where you sit on the curve in the class. Okay? I guess I'm not going to say too much about grades at this point. This is more relevant once we have the first midterm. So I won't talk about this now, but you can read through this and know exactly what will be done to calculate grades, even now if you care. How much should you care about grades? You should care because to take prelims, if you're in the PhD program, you need at least a 3.5 GPA. If you're an MEng, maybe that's a new program, so I'm not sure, but employers may care about your grades if you're an MEng. If you're a PhD candidate, though, and you get a PhD, no one will care about your grades. I'll tell you that much. No one will care. They'll care only about your research if you get a PhD. All right, but if you're getting a PhD, you better care about your grades because you can't take prelims without a 3.5 at least. Okay? Maybe I shouldn't even said that about no one cares about your grades. You should. Right? Just as a matter of pride. But don't let your grades consume you too much, right? That's all I'm going to say. All right, so any questions regarding logistics for the class? Those are all, yes? It's group, actually. It's always been group. So usually 3 people get together to do the project. And what it is it's been a presentation. Well, it's been different for different years. So sometimes it's been both a write-up and a presentation. Sometimes it's just a presentation. And so PowerPoint presentation, oral presentation, sort of to make sure that you know how to give a good talk, I suppose. Okay? I would say the project in this class is a lot milder than others. There are some classes that are truly horrendous when it comes to projects. This is not one of them. Maybe I should make it horrendous to make sure you work on this one, because that's what happens. When you have a really bad project, you spend all your time on that, and then you don't spend much time on the project that doesn't take that much work. Yes? Are you going to do microfabrication? No, there's no lab component to this class. So most of our graduate classes don't have lab components. It's the undergraduate classes. If you want to do fabrication, 143 is the class to take. 143 actually fabs NMOS transistors plus MEMS devices that never work because of stress issues. They work. You get MEMS devices, but they curl up all over the place. Okay, in 143. They don't learn enough in 143 to understand all the stress issues. You'll learn that here. But there's no fabrication component to this class, right? There's no lab to this class. Unfortunately, you'll get that experience doing research if you're doing MEMS research. Okay? Any other questions? All right. Okay, so let's go ahead and start the true lecture material for this class. I guess we end at 3:30. And so let's get back to this and this. All right, so this lecture here is going to be sort of talking about definitions for MEMS, looking at a roadmap for MEMS research. That's always interesting to look at to see which directions people are heading to do new things, and then starting to talk about the benefits of miniaturization. And so that's an important thing. Why do people do MEMS at all? People do MEMS because it increases performance by orders of magnitude when you shrink things. I think a lot of you, at least the EEs, well, everyone knows, right? You shrink a transistor, you get much better performance. That's certainly true over almost all the different physical domains. Mechanics, chemistry, bio, all of these things. You will get something that really looks good. Something may go bad, like I said. But if you can suppress that and take advantage of what really looks good, you can increase your capabilities in huge ways. And I'm going to describe how that happens in the following slides here. So I'm going to do this by slide because it's mostly just me talking. Again, later on there's going to be a lot of writing going on as well. Okay, so what are MEMS? Microelectromechanical systems. And so one definition for MEMS that people have used is a device constructed using micromachining technology. That is a very broad definition, right? If that were the definition of MEMS, then a FinFET is a MEMS device. Okay? And so some people actually believe that, but you know, I come from a funding agency. I spent some time at a funding agency, and when you're funding things, you have to bin things, right? You can't say that I'm funding everything in my area, so you have to bin things. And so at least at a funding agency, a better definition may be something like a microscale or smaller device or system that operates mainly by way of a mechanical or electromechanical means. So there's some kind of mechanics in this, in its operation. And so one way you could do this is just make sure that at least some of the signals that flow through a MEMS device are best described in terms of mechanical variables. So those in EE, right, you know your signals. They're voltages, they're currents. Pretty boring. Well, no, not boring, but if you've worked with them too much, then you may want to expand that beyond, right? And so there are mechanical variables that also serve as signals, right? Displacement is a signal. Velocity is a signal. Acceleration is a signal. Temperature, flow. There's all sorts of signals out there, and you actually can use each of these to do computation if you needed to. Okay, so in a MEMS device, you're accepting these other signals to go through. So if I wanted to create a schematic of a MEMS device, I may create something like this. If you're an EE, yeah, it looks just like a transistor, right? But you know, you sort of say that some of the flow variables through this, right, could be voltage or current, but they could also be acceleration, velocity, even light, heat, that sort of thing. So very general things flowing through this. And they've got some control variable, which could also be voltage current, but could be all of these other generic variables as well, where this control variable acts through a transducer that converts that variable to some kind of mechanical motion or some kind of mechanical phenomenon or so that allows this variable to pass through. And so one Concrete example of this is a micro-optical table. This is an example from Professor Ming Wu when he was at UCLA. He, of course, is now here at Berkeley. But this is an optical table, and so you can see the laser light going through this. This is a mirror. This is a Fresnel lens. And this is processing the signal, and by mechanical means, through some kind of transducer, use a voltage to, say, pivot this mirror here. You can change the direction of that laser. Okay, so that's a good example of how this definition fits a very good MEMS application. All right, some other attributes from MEMS. The feature sizes are measured in microns or less. And so MEMS is kind of a thing, right? We still call microelectronics, right? But indeed, the scales of microelectronics are truly nano now, right? We still call them microelectronics. MEMS is the same way. We're still calling MEMS as microelectromechanical system, but that is also including things that are even going down to the nano scale now. Okay, and just some example of how things shrink. This is an example of a gyroscope. And so I don't know how many people know what a gyroscope is, but this is something that can tell you which direction you're pointing. Okay, why is that important? Where if you're on a ship going across the ocean, if you're flying across the ocean in a plane, you got to have some device that tells you which way you're pointing. Otherwise, you're not going to know where you're going. Okay, especially at night, right, where you can't see anything. You got no reference point. You need that sensor to tell you which direction you're going, to navigate. Okay, that's what a gyroscope is doing. Incidentally, you all have gyroscopes, I'm sure, because you all have phones, right? And so your phones are now using gyroscopes. When you rotate your phone and suddenly that screen rotates for you to look correct, that's a MEMS gyroscope doing that. Okay? Your automobiles are now starting to use MEMS gyroscopes as well to do skid control. GPS has always used things like accelerometers and gyroscopes because when you lose that GPS signal, you now rely on these mechanical devices. Say you go into a tunnel or go into a parking structure. Okay, so these devices are now everywhere, but if they were all this size, which is what they were before MEMS, so this is what, 80 millimeters, they would not be in your phone. They would not be anywhere. Right? It took shrinking everything using MEMS technology, using a structure maybe like this, which is no longer a spinning disk or so. This is now a vibrating structure, using kind of a different principle for the gyroscopic sensing here, but now being made in a very tiny size. This is an example from Khalil Najafi from the University of Michigan, who I worked with for a long time. This is showing how you can get this together with circuits here, signal conditioning circuits. And that then shows another thing you can do with MEMS. Not only shrink the size that makes it cheaper, that makes it deployable in many applications, many portable applications, but also it makes it very convenient to merge computation with the sensing. So often the MEMS device does sensing, the transistors does the computation for you. And so this actually allows us to change the way we perceive and control the physical world. So this revolution that's going on, that's using sensor networks and that sort of thing, a lot of that is predicated on the ability to have a sensor technology that can be very small, very low power. MEMS technology is one of the technologies that is making that happen. Okay? Another common attribute of MEMS is that it uses planar lithographic technology for fabrication. You can use fab equipment identical to those needed for integrated circuits. So if you have a semiconductor processing fab, you can do MEMS. And that's what you're seeing across the world right now. People who have foundries and semiconductor processing, they're looking more to MEMS because it's harder these days to make money in ICs. Right? The fact that your phone is so cheap, your computer is getting so cheap now, is not something your semiconductor foundries are happy about, but that they have to put up with. Right? They do a lot of work to put something out that they no longer make that much money off of. So they need more products to make money off of. MEMS is one of those products that they're looking at. So if you look at TSMC, they're starting up a MEMS area. Right? A lot of these foundries are starting up MEMS. So this is a nice course to take because you're going to understand more, probably what the bigger set of products will be coming out to the future. So you can use fab equipment identical to those for ICs. However, some of the fab steps transcend those of conventional IC processing. So as a matter of fact, there's some things that people are doing in ICs, like people are trying to make 3D integrated circuits. They're taking wafers, bonding them together, doing through-wafer vias and that sort of thing. That technology was actually developed by MEMS researchers. Right? So what's happening is MEMS borrowed from IC technology in the beginning, but now there's a lot of back and forth. We're borrowing from each other, and that's probably the best way the world can work. Right? Okay. So how do we make these MEMS devices? How was this device made? So what this device is, this is the anchor point. Okay, these are actually electrodes. They're also anchored to the substrate. All the stuff that you're seeing here is suspended above the substrate. And I guess it's hard to see that because the gap between it and the substrate is so small, but it's actually suspended above the substrate. Yeah, you can't really see that. You can't see the shadow in that. It's suspended above the substrate and it's free to move. Okay, so this whole mechanical structure on the inside here, these springs, this ring that you're seeing there, free to move. And it actually moves in a mode shape that looks like this. Okay, that incidentally is the same mode shape that when you're at a dinner and trying to get someone's attention with your wine glass and your fork, right? That sound that's being made, that's the mode shape this makes. That's why this is called the wine glass mode shape. Okay, and it makes that piercing sound that cuts through everything that everyone can hear and you get their attention. Okay, how was this made? Okay, this was made using planar processing. So you start with a silicon substrate. You use a technology called deep reactive ion etching, which is a technology used to do this through wafer stuff that was really developed for MEMS, right? To etch very deep into the silicon substrate. Very deep, very straight sidewalls. We will talk about exactly how this works in this class. You then do a similar thing to a glass substrate, where you etch, say, anchor points for this structure. So this kind of defines a structure. You can't see it yet. Right? You then flip this wafer, you put some interconnects on this glass substrate. You then flip the wafer over and you bond it to the glass. This is done through a process called anodic bonding, where you can actually get things bonded up such that they stick with very high strength. Okay? You then dissolve away the silicon substrate, the top of it, so that you now end up with places that are anchored to the glass right here and things that are actually suspended above the glass that are now movable. That's exactly how this was made right here. Okay, so you can already see something here. We're not limited to semiconductor materials. I didn't have to use silicon. I could have used something else that I could have etched. Okay, so that's another strength of MEMS, and that you can use almost any material. That opens up, the applications for MEMS sensors to even harsh environment things, right? If you want to sense, say, inside the engine of an automobile, which may be a good thing to do. This is research that Al Pisano is doing in mechanical engineering. You may want to do that to try to improve, say, the efficiency of which you're using the gas in your car, right? So that's a very green type project here, to get a MEMS sensor inside your engine in your automobile. And you can only do that if you're using materials like silicon carbide or so that can withstand that high temperature combined with oxygen at the same time. This is also another example from Al Pisano. This is a micro rotor for a micro engine made using a bulk micromachining technology, not this, but something similar where deep reactive ion etching was used. There's also another type of fabrication technology called surface micromachining. This is more like what people do with integrated circuits. This is the technology where if you have an IC fab, you could do this. Okay, and I even showing this in the context of putting MEMS on top of ICs. So here's the cross-section of an integrated circuit. This is a CMOS transistor there. And in order to put MEMS above this, you just continue to do things that you can already do in CMOS, which is put layers down, do etching again and again and again. So go ahead and etch maybe a via down to this jumper that connects the metal from the CMOS transistor to the MEMS device. Put down a layer of polysilicon, dope it and pattern it to make it conductive. This is now your MEMS type of interconnect, electrical interconnect. Then put down a sacrificial layer. Sacrificial layer because it's only going to be there temporarily. It's only there to support the later things that we want to put down. Maybe etch a via into this sacrificial layer that serves as an anchor. Finally, put down your structural layer and pattern it, dope it if necessary, so that you end up with this cross-section where your structural layer, which you want to free, is temporarily suspended, supported by the sacrificial oxide. And once you've achieved this cross-section, the final step is to put this into hydrofluoric acid solution, which will remove the oxide preferentially, not attack the polysilicon or the nitride above this here, and leaving you then with a freestanding beam. This is the process that is used, I guess, for a large fraction of the MEMS products that are out there. Okay, very simple process. This was a 3-mask process that we just went through here. Okay, very simple, but not so simple if you don't understand stress and strain. Okay, so if you don't know what you're doing, you can do all these steps. And if you just went into an IC foundry and did all the steps in an IC foundry, you would not end up with this. You would end up with something that looks like this, with maybe anchored here, but this beam would be bending up like this, or might be bending down. Or maybe the beam is not even a contiguous beam, it's falling apart because it's just grains that are falling apart. Okay, so I can tell you, when I started my company, DeSera, they actually put out products exactly based on this process here. They're oscillator products. You probably have one in your TV or something like that. They sell a lot of them per month. Millions per month are being sold of these oscillators. They're very simple products. Very small margins, so don't think I'm a rich dude yet. Okay, so they're very small margins, but the thing is, it took 6 years to try to get an IC foundry to run this process. Right? When the company started, there were no MEMS foundries. So we had to teach an IC foundry to do this. It was a 3-mask process, but 6 years to get to the point where they could actually run this with enough yield. And that's because they had to understand things that you're about to learn in this class to make it work. Okay? Here's an example of a device made using exactly this technology that I just showed you. So you can see the CMOS electronics here integrated together with the micromechanics. This is a folded beam resonance structure, which you'll learn about in this class. It's basically this mass here, this shuttle mass we call it, that's suspended above the substrate by 2 microns. Okay, all of these supports, you can see this folded flexure is suspended also. The only anchor points are right here and there. Okay, 2 anchor points for the whole structure. The whole thing can move back and forth this way. And this is basically a feedback loop with an amplifier that sustains oscillation. This is one of the oscillators that some companies are selling right now. Well, actually not this one just yet, but intend to sell for your 32 kilohertz clock oscillator. When that becomes a product, boy, everyone will have MEMS, right? Your watch, your cell phone, which already has MEMS, everything will need it. Because if you think about it, all electronics need some kind of timing device. Right? So this could be a huge, very high volume product, but very small margins. Right? So you don't make a lot per product on that. So this worked. Right? This is an oscilloscope waveform for this, but just proving that this works. But how difficult is this to do? Why is it this is not a product yet? It's not a product because there are temperature issues with this. So in order to put this micromechanics down over these circuits, you needed processing temperatures greater than 600 degrees C. That's about what it takes to put down polysilicon. Transistors can't take 600 degrees C. Well, transistors can, but their metals can't. Okay? And so this is a bit deceiving because the metal being used here is tungsten. It's not aluminum, it's not copper. Okay, and so this is a lesson to be learned, right? When this work was first done, a lot of people were saying, oh, okay, now we're going to integrate MEMS together with transistors. But no, never happened. Why? Because your integrated circuit transistors use aluminum and copper for their metal. They spend billions of dollars to develop multi-level metallization processes, right, where they can get 12 levels of metal or so above your CMOS circuits. They're not going to change that metal process to go to tungsten just so this MEMS device can go on top. Okay? It could be a very good product, but no one's going to do that. Okay, so the lesson to learn is that ICs will not change for MEMS. MEMS has to change for ICs. Okay? ICs still rule. Okay, so what's happening is people are investigating different ways to put down MEMS materials at lower temperatures. Okay, so that's a lot of research going on in my group. Al Pisano's group is doing a lot of that. A lot of people working on this to try to get ICs together with MEMS. This is another example of the cool videos, I guess, you can get with MEMS technologies. Another example from Ming Wu, where basically what's being applied are voltages here. And these voltages are exciting an actuator that is physically moving this structure up. And so you can see the spring between that there. This is kind of an inductor, but not a good one, because if you shake it, it's like a slinky or so, right? The inductor value will change too much. But this is just one of the cool things you can do with MEMS technologies. It's very photogenic. And so now how about roadmaps for MEMS? And so this is the way people were thinking, I guess, before I went to DARPA, which was about 2002 or something like that. They were sort of thinking that the way to think of MEMS and how good the MEMS part is sort of count the number of transistors you can get together with the MEMS components. It was sort of agreed upon by a lot of road mappers that if you could put more transistors together with more MEMS, that's the better MEMS product. Okay? And so everything up on this side of the scale, where this is number of transistors, that's number of mechanical components, everything up here was the best MEMS part. And that's what was fueling research funding for MEMS during those years. Okay, you could sort of see some of these things, right? The digital micromirror devices, which you know are being used in TVs and also in those huge theaters that you have, HD theaters or so. And so why was it that people kept marrying MEMS together with transistors? Well, a lot of it was because a lot of the initial work in MEMS was done by EEs. Okay, there were very few mechanical engineers doing MEMS in the old days. It was all EEs, and why is that? It's because EEs were doing a lot of the fabrication technologies that could make many things on a single chip. Okay, now the field is not dominated by EEs. There's an equal number of EEs, MEs, chemies, physicists. Everyone is there. That's why this class is the way it is. We want everyone to be able to get in and learn some of these things. So the number of mechanical components people were equating to the ability to sense, to act. Okay, right? Use these mechanical things to sense. Use the transistors to compute. And one really good example of one of the first MEMS products that really was based on this kind of thinking is the analog devices 80XL78 or 80XL50, the 80XL line. 80 stands for analog devices, XL stands for accelerometer. So what an accelerometer is, it's a device that detects acceleration. Why is that such a good thing to have? Well, in your Wii device, when you move it like this, right, you need something to detect that you've moved it like that. So something had to detect the acceleration. Something also had to detect which way you're pointing. So not only do you have an accelerometer, but you have a gyroscope in that device. In your automobile, when you crash, what tells the airbag to deploy? You have to have something that says, "Ooh, my acceleration just went to an enormous negative acceleration." And once you hit that negative acceleration threshold, out comes the airbag. Okay, something has to detect the acceleration. It turns out that the devices that detect the acceleration in automobiles are all MEMS devices now. Okay, and they all look something like this. So the principle of this is you make a mechanical device, now a tiny mechanical device that's suspended by some kind of spring support that's attached to some kind of chassis. Okay, when this chassis experiences an acceleration, say in this direction, what you get is an inertial force, you know, on this proof mass that will push the proof mass in that direction. Okay, well, all of a sudden you have changed the distance between the proof mass and the chassis. Okay, you can measure that change in distance by measuring the capacitance between these two. There's a number of other ways to measure that change in displacement. But that displacement then becomes your main output for this. And that displacement is proportional, of course, to the force, which is then proportional, the force that's generated, the inertial force, proportional to mass times the thing you're trying to detect, acceleration. Okay, so that's how you're turning acceleration into your output variable. But you see a problem with this? The scaling factor for that acceleration, right? You want that output variable to be as large as possible because you need it to be above the noise of the sensing electronics. But if I'm going to scale that mass, if I'm going to use MEMS to make that mass smaller and smaller, my scale factor suddenly has gotten smaller and smaller, and now I can't sense as much acceleration, right? The minimum detectable signal has gotten worse because I made this thing smaller. Okay? So this is a case where smaller is not better, smaller is worse, and much worse. Yet people still do it. Right? They still do it, and they can do it because if you can integrate this together with electronics, you can delete a lot of parasitic capacitors that then allow you to sense very small motions. And so that's the whole crux of combining MEMS with transistors. Okay, this is what fueled it all. Right? People wanted to make accelerometers. They understood that when you made the accelerometer smaller, the output got worse. So you had to integrate with transistors to maintain the same performance as the big accelerometer. Okay? That's still true today for accelerometers. It's one of these applications where making it smaller doesn't help you on the performance side, but boy, does it help you on the deployability side. Right? It's now everywhere. Boy, does it help you on the cost side. They're so cheap now. Okay? It also helps you in some other performance parameter, which is G-force resilience. Okay? So these accelerometers can now stand up to very high G-forces. Right? If I drop this from that level, that's a lot of G-force. That's 1,000 Gs or so that I just applied to this pen here. A lot of things that take 1,000 Gs, they break. These things won't. Okay, so that's one of the performance boosts And I also described one of the things that went wrong with performance. Okay, so over time, even though this was the roadmap, actually that DARPA was using to fund a lot of MEMS technologies, thinking that you had to get them together with transistors, quickly people were seeing that making things smaller actually helped performance in a lot of ways. Okay, so gyroscopes, or another thing like accelerometers, where making it smaller doesn't necessarily help you. Okay, but other applications like microfluidics, making it smaller can help a lot. It helps a lot because, one, the analyte size could be much smaller, right? They don't have to take a whole test tube of your blood, right? You can just prick your finger, use that blood, and then let this MEMS-based system analyze it for you. Okay? A lot of glucose sensors are sort of made using this type of technology now. Also, when you make things smaller, things just go a lot faster. Fluidic type processing goes a lot faster. So things that you could have done, DNA analyses or so that people take days to do, can be done much faster using a MEMS type sensor. Also, mirrors. Right? There was a whole optical switch, cross-connect switch industry that was about to form before the telecom bust, I suppose. There was a lot of people prepared to make a lot of money. A lot of people did make a lot of money by selling their companies early enough before the bust. Okay, but there's a technology where switching mirrors can be used to switch the optical signals used in telecommunications. And this could have been a huge industry, but the reason why this works so well is that the smaller you make that mirror, the faster you can switch it. And suddenly it can be used in a lot of these fast switching type applications. That's also true for the digital micromirror device, which you know has a large industry already. Television sets, HD TVs, IMAX theaters, that sort of thing, based on this kind of technology where you have thousands or millions of these mirrors here that can be tilted, switched to push light in different directions here. Right? Not only can you make them small such that they can fill the area with a very large fill factor, you can also move them extremely fast just because they're small. Okay, so what you're seeing here is that smaller is in fact better, a lot better. And people were beginning to realize this. They were also beginning to realize that increasing ability to compute, the more transistors you have, the more energy you're consuming. Okay, a lot of mechanical things can do the same thing a transistor can do, but without consuming as much energy. Okay, and so people start to realize that this is lucrative territory down here, that getting lots of mechanical elements in a very small size can give you huge performance boosts. And so I'm about to talk about some examples here of how scaling things down in size, beyond the examples I just showed here. We'll go a little deeper into some examples here. But let me just say this. The benefits of size reduction is really what MEMS is all about. Okay, so it's clear how shrinking things in integrated circuits gives you better performance, right? It gives you faster speed, lower power consumption. You can get larger functions because you get more complexity. Economy is better. Things get a lot cheaper. MEMS enables a similar concept, but it does it beyond just the electrical domain. Okay, so think of this as scaling just beyond the electrical domain, enhancements for application domains beyond those satisfied by electronics. Some examples here. So speed. You make something smaller, its frequency goes up. Okay, so in my research, that's what it's all about. We're making things smaller and smaller. We have mechanical things going faster than you can get transistors to go now. Right? Mechanical things are up in the tens of gigahertz or so, and they don't need a lot of power to operate. Thermal time constants also faster. You make something smaller. If you have to heat it up, you can heat it up instantaneously now. Okay, you're not waiting 30 minutes or so for this oscillator to stabilize. It happens in milliseconds. Okay, just because things are smaller. Power consumption. Actuation energies go down, heating power. That example again, if you have to heat something, and a lot of sensors require heating. Okay, to do the sensing correct, like gas sensors, it's best to heat these things. Well, if you have a macroscopic version of it, you're going to be expending a watt of power or so. The MEMS version, maybe milliwatts of power. Okay? Complexity. The integration density goes up, which means your functionality goes up. So this is the thing where MEMS designers really have to understand circuit design to make circuits of MEMS to get better functionality. Economy. These are all batch fabricatable on the wafer scale. If you can especially batch fabricate your packaging, you can make things a lot cheaper than the macroscopic scale version of things. And robustness. When you make things smaller, you actually can take larger G-forces. So that's kind of counterintuitive. You think smaller things are weaker. No. they're actually stronger. As long as you don't come in and physically hit it, right, then you're going to destroy it, right? But if it goes under very large accelerations, it's going to survive more and stay more stable than the macroscopic version of whatever it is. Okay? I can keep going with this. There's all sorts of advantages that you can find just by making something smaller. But I guess what I'll start with is an area that I do a lot of research in, and that's vibrating RF MEMS. Okay, so what's this about? So this is all the same as scaling a guitar string. Okay, so we all know guitars, right? We all know that if I take a guitar and I tune one of its strings to an A, so take the A string, that A is 110 hertz. That's what you're hearing. It's a very low frequency. And if I were to plot the vibration amplitude of that plucked guitar string versus frequency, it's going to look something like this. Okay, it's going to resonate at this very specific frequency, 110 hertz. And at all other frequencies, it's not going to move as much. And that way, it's rejecting all other frequencies, and it's selecting just 110 hertz. Okay, and it depends on how good that guitar string is. There's a lot of design in this, right? If you have a brand new guitar string, doesn't have any oils from your fingers on it, it loses very little energy. Okay, so it has a very high quality factor. After you've played it for a while, a lot of dirt, oil, grime gets onto it, suddenly your cue, it's no longer as selective. Okay, it loses energy, which means it's no longer as frequency selective. We'll talk about a lot of this in great detail later on in this course. But if you look at this transfer function that's selecting a frequency, what else is this needed for? It's needed for almost everything else, right? Our ears are basically hearing things that are filtered for us, right? That's what music is. But that's what your phone is doing too. Right? Your cell phone is doing exactly the same thing. It's picking up a specific frequency, just not at 110 hertz. It's picking up that frequency all the way up at hundreds of megahertz to gigahertz type frequencies. And that's what we're transmitting electromagnetically. That's what's going through the airwaves. Okay? But as soon as that signal hits your antenna, it needs to be processed. It needs to be filtered. Right? Because we're transmitting information at all frequencies from 100 megahertz to 3 gigahertz and beyond, actually. Right? If your antenna is picking up all those frequencies, how are you going to figure out which one belongs to your conversation as opposed to someone else's? Right? You've got to pick one frequency, and that's what this is doing. Okay? So the question is, can we get that 110 hertz to gigahertz? And the answer is absolutely. And you know how it's going to be done. Scaling. Right? Make it smaller. Okay? If you make it smaller, fundamentally for mechanics, the frequency at which something vibrates, and everything has a resonance frequency, right? There's going to be a frequency at which it vibrates. It's all determined by what it's made out of, what its dimensions are. But inevitably, if you make the dimensions smaller and smaller, frequency will go up. And basically, it comes down to stiffness divided by mass, where you could see mass directly in that equation. If I make it smaller and smaller, I'm pushing that mass smaller and smaller to the point where I can now make a micromechanical version of that guitar string. It's not quite a string, it's more a beam here. But instead of this 25-inch long string made out of a metal, it's now a 40-micron long beam that's made out of polycrystalline silicon, which is an IC-compatible material. It's 2 microns thick, it's 8 microns wide. Instead of plucking it into vibration, it's now driven into vibration electrically using an electrode that is underneath the beam by about 100 nanometers. Okay, so there's a tiny gap between this beam and that electrode. Okay, so just by applying an AC signal here and tracing the output amplitude versus the AC signal, this now traces out this frequency selective transfer function, exactly what we need for wireless communications. Not quite at the gigahertz frequency that we want, but you could see that making things smaller does increase that frequency. And to get the gigahertz frequency, I'll show you how to do that a little later on. But a couple things that are interesting about here. Okay, at this 8.5 megahertz, the quality factor is 8,000. Okay, what does that mean? That tells you how selective this is. And so to give you an idea of how selective that is, if you take a transistor circuit and you use the inductor that's available in your transistor technologies, what Q will an inductor give you? Spiral inductor in an integrated circuit transistor technology. Does anyone know? EEs? 5 is respectable. You're lucky if you get 10. Okay? This is 8,000. And that has to do with mechanics versus electronics. Okay? In mechanics, right, quality factor is sort of energy per cycle divided by energy loss per cycle, the energy per cycle in mechanics is a lot higher versus the energy loss. Okay? The losses in integrated circuits and electronics are just too large. Okay? That inductance divided by resistance is compared to stiffness divided by damping, where stiffness divided by damping in mechanics is much larger. Okay? So there's the advantage of mechanics right here. That's one advantage. And then making it small gets you to the frequency that you want to be able to work at. Whoops, we are over time. So we'll end it right here. And what I'm going to do next is actually derive the frequency equation that tells you how to get to the high frequencies. Okay? And I guess you will have discussion on Monday, so attend that, at least to see Henry and what he has to talk about.